Welcome, everybody. So today we're going to talk about magnetic induction and Faraday's law, which I've mentioned in class already. The way that magnetic induction works, if you need a quick reminder, is that any change in the magnetic field will cause an induced electric field. Now, there's some profound vector calculus behind that. You can actually see one of Maxwell's equations over here that we won't talk much about in this course, which says that the curl of the electric field is equal to the time derivative of the magnetic field. That's ultimately where all of this comes from. But we don't want to really dig into the vector calculus in this course. So we're going to use a slightly modified statement here, which is instead of looking at the induced electric field, we're going to look at the induced voltage around some closed loop. And when we do that, what we see is we get that the induced voltage is going to be the negative time derivative of the magnetic flux through that loop. Now we know how to calculate magnetic flux from last week, so all we have to do is figure out what the flux is, take its derivative with respect to time, throw a negative sign on there, and we've got the induced voltage around some loop. If you need a reminder about how to calculate flux, it's right here. You just take the magnetic field, dot it with the area vector, and then integrate over the full area of the loop that you've got. So that is fundamentally how Faraday's law and induction works. This is really the only rule that we're going to use for like the whole next week. And we're going to be able to use it in a wide variety of situations. I think I've shown this slide to you as well, but I want to kind of reiterate what's going on here from kind of a fundamental perspective. It really is an induced electric field. Right, so you can see that there's this region where the magnetic field is increasing, so going from small to large. And then what that does is it creates a little electric field that points kind of curly around this circle. And when you've got a current, or sorry, when you've got an electric field that's going around like this, that's going to cause current to flow if you put a piece of metal there. Don't put a piece of metal there, the electric field is still there. The voltage induced around the circle is still there, but there won't be any current flowing because you don't have a conducting path. All right, I want to do one example of this using our magnetic induction table. So I've pulled a simple example from the textbook, which has a magnetic field, which is pointing out of the board at us. That's all the little blue dots, and has a rail, a kind of gray rail that's moving upwards on top of some copper metal wire. And so you can see that we've got a change in the magnetic flux in this example. So we are going to go ahead and make a magnetic induction table. I'm going to go ahead and draw us a little table here. So these guys are really simple. We just need a whole bunch of rows to start doing some of these calculations. All right, that's probably enough. So I always want to start out by thinking about what our area vector looks like. So here's our area vector. I'm going to go ahead and look at the thing, right? So here maybe is my loop that's formed by the copper wire on 3 sides and then by the gray wire on the 4th side. That wire is oriented like this. So my choices for the direction of the area vector are into the screen or out of the screen. I'm going to choose what is usually easier for me, which is to pick the vector that points in the same direction as the magnetic field, if I can. So that would be out of the screen. So that would be a circle with a dot to it. And I'm going to go ahead and do this both like qualitatively and quantitatively here. If I want to know what the actual size of this vector is, well, I'm going to need to give a name to these things. So I'll call this height y. That's going to change as the gray wire moves up and down. And I'll call this length x. So this area is going to be x times y. That'll be the length. The next thing I want in my table is the magnetic field. And that's given to me, right? It points out of the board, and its magnitude is just b, right? Maybe I'll add a quick, this is the direction, and this is the magnitude. All right, next thing I want to do is calculate the magnetic flux. Magnetic flux, like so. And magnetic flux, I know, is the dot product between the area vector and the magnetic field. So in just thinking about kind of direction, and actually I should modify my little thing. This is direction flux sign, right? Because flux does not have a direction. Move that over there a little bit. So let's see, the magnetic flux here is going to have a magnetic field that points in the same direction as the area vector. That's a positive dot product. So I'm going to get a positive flux. The size of that positive flux is actually going to be pretty easy. This is a uniform magnetic field, doesn't change from top to bottom or from side to side. So I just have to multiply the magnetic field times the area. B times X times Y, and again, it's positive. The next thing I have to do is take the derivative of this thing, right? So I need to take the derivative of the magnetic field, d t. There we go. And again, I'm going to do this qualitatively first. It looks to me like the flux is decreasing, right? It's going from large to small because the area is changing. The magnetic field is constant, but the amount of area that the circuit is exposed to is decreasing. So this is a negative change in the flux. I can also figure out how big it is by taking the derivative of this thing. That's not that hard. B is constant. It's not changing in time. X is constant. The width of this circuit is not changing in time. So all I have is B times X times dy dt. Dy dt, we remember all the way back from our first introductory physics course, is just the velocity of the rail in the y direction. So I'm going to write this as B times X times Y, times V sub Y. All right, the next thing that I want to have in my table is the induced voltage around the loop. And that's pretty easy because all I do is throw a negative sign on here, right? Faraday's law says throw a negative sign onto your change of flux. The change in the flux is negative, so I'm going to get an induced voltage, which is positive. I can figure out how big it is, again, by just taking the answer that I've got here and throwing a negative sign on it. I didn't copy the negative sign over here, so I'm just going to go B at B sub Y, right? All right, last thing I want to do here is find the induced current in this wire. I'm going to go ahead and assume I know the total resistance of the gray wire is R. I'm going to assume that this copper wire here is an ideal perfect wire that doesn't have any resistance. So if I do that, direction-wise, this is probably the trickiest step of using the magnetic induction table. You have to think about what your coordinate system is. And to do that, you've got to go back to your area vector. We chose an area vector which points out of the board. So using my right-hand rule, if I curl my fingers in the direction that I get with my thumb pointing in the direction of the area vector, I see that counterclockwise for me is a positive current. If I flip my thumb around and point opposite the area vector, now I would say clockwise is negative. So I have a positive voltage induced. That's going to give me a counterclockwise current. So I'll just draw a little arrow for that. Counterclockwise current, which is the kind of this way in the circuit. And I can figure out how big it is by taking the voltage and dividing by the resistance in the circuit, right? So I decided there was some resistance R. So this is going to be VXVY divided by R. Let's see. There's one more thing I can put in my table, which is the induced magnetic dipole moment of the loop. We know a current carrying wire or a current carrying loop is going to have a magnetic dipole moment. That's going to point again, kind of right-hand rule-wise, in the same direction as the area vector if I have a positive current, and opposite the direction of the area vector if I have a negative current. Here I have a positive current going this way, so this is going to be an outward pointing magnetic moment. If you want to know how big that is, let's see. The magnetic moment size is I times A. So I would take this Bx Vy over R and multiply by the area again. So I would actually get, let's see, Bx squared Y V sub Y divided by R. So that one gets a little complicated, but you can think about it as a little bar magnet that has its north end coming out of the board at you, south end going into the board. All right, so that is how Faraday's law and magnetic induction works with a nice little example. We're going to do some more of this in class this week.